Section 5.2 is about one of the probability distributions. This distribution is called binomial distribution. Now the question is, what is the binomial distribution and when can we say that a given probability distribution is binomial? Here we have some conditions or requirements for a probability distribution to be binomial. We have four basic requirements. The first one is that we have fixed number of trials. For example, tossing a coin twice, we have fixed number of trials that's equal to 2, and the number of trials is denoted as n, so n equals 2. The first condition is satisfied. That's fixed number of trials. The second thing is that trials are independent. For example, here when we toss a coin twice, in the first toss we may get head or tail. In the second toss we still have the same possibility, head or tail, but if you get a head in the first toss, that will not affect the chances of getting head or tail in the second stage or second toss. That means they are independent. So the second condition or requirement is satisfied. The third one is that each trial must have all outcomes classified into exactly two categories: success and failure. So here we can classify the outcomes into two categories. Actually, we only have two outcomes, either head or tail. So since we have two outcomes, that means the third requirement is satisfied. Now the fourth requirement is that the probability of a success remains the same in all trials. So for example, in the first toss, the probability of getting head is 1/2. The probability of getting tail is 1/2. In the second toss or second trial, we still have same probability. Probability of getting head on the second toss is 1/2. Probability of getting tail is the same thing. So probability of success of getting, if we are worrying about or if we are observing the event that we get, for example, two heads. Let me define it here. X is number of heads, and we are interested in determining the probability of getting, for example, two heads. Then the probability of success is always the same. Let's take some examples. The first example here talks about some scenarios or some experiments, and we want to determine whether a given experiment is binomial or not. For example, here when we have 291 couples use some method of giving birth, and they get the method Y sort and give birth to 291 babies. So we have how many trials we have? We have 291, and the weight of babies are recorded. But we know that here we don't have two outcomes. We may have more than two outcomes for the weight of babies. So each of the weights has more than two possible outcomes. So this is not a binomial, because we have more than two outcomes. But if we modify this experiment and we just focused on the genders of the babies that are recorded, we only have two outcomes here, either male or female. So that means this is a binomial. Yes, it's binomial because the four conditions are satisfied. N is fixed, number of trials is 291. check each baby, every baby in this experiment to see if that baby is male or female. So we do the experiment 291 times, and then the second requirement is that they are independent. If we check the first baby and the baby was a girl, the second baby can be a boy or a girl. It will not be affected by what happened in the first experiment or first stage of the experiment. So that means trials are independent. So the second condition is satisfied. The third requirement is that we only have two outcomes, and that's correct. We have either male or female. And the fourth one is the probability of success remains the same. For example, probability of getting male is 1/2. Getting female is 1/2. And this is still the same for all the stages or trials of this experiment. So the four conditions are satisfied, and we call this binomial. By the way, when we read binomial, bi means, when you read bi means two. So binomial indicates that we have two outcomes. Now the third case, in an Idaho Potato Commission survey of 1,000 adults, subjects are asked to select their favorite vegetables, and each response was recorded as potato, potatoes, or other. So we do this experiment 1,000 times. That means n is fixed, number of trials is fixed, and whether the first one choose potatoes or other, the second one can choose any one of the two options, or the third one the same, fourth one up to 1,000 adults. So they are independent, trials are independent, and we only have two outcomes, either potatoes or other, and the probability is the same, 1/2, for example, 1/2, and so this is yes, it's binomial. Now what about D? Same experiment, but we are interested in, our subjects are asked to select their favorite vegetables, and each response of potatoes, corn, broccoli, tomatoes, or other. So we have more than two outcomes. So this is not binomial because we have more than two possible outcomes. Now let's come to the probability of binomial distribution. If we know that a distribution is a binomial distribution, then we can find the probability, we can compute it in some method. So we need first to define the simples, the following simples. Probability of success, P of S denotes success, is little p. So when you read little b, that means probability of success. Probability of failure, P of F, is the complement of probability of success. I mean by complement, 1 minus probability of success. And this is denoted as Q. And N is number of trials, as we've seen before. X represents number of successes in N trials. For example, if you are interested in having 3 babies, and after testing, for example, 10 cases, so that's number of successes. Now little b, as we've mentioned, it's probability of success. Q is probability of failure. P of X, probability of getting exactly X successes among the N trials. We will see some examples that explain these things. Now in general, if we have some experiment, if this experiment or sampling is done without replacement and the sample size is no more than 5% of the size of the population, then we treat the selections as being independent, even if we are almost sure that they are actually dependent. But for purposes of computations, we can just consider them independent. Now let's take another example. Here in this example, we ask some people, or when adult is randomly selected, there is 0.85 probability that this person knows the Twitter, what Twitter is. So then suppose that we want to find the probability that exactly 3 out of 5 adults, randomly selected adults, know what a Twitter is. The first question is, does this procedure result in a binomial distribution? Here, in order to answer this question, we need to check the 4 requirements. The first, we want to see if number of trials is fixed. Number of trials is 5. So n is equal to 5 because we have 5 people who were asked that question. The second thing, they are independent. So we can say that they are independent because if you ask the first person and he answered, yes, I know what Twitter is, then the second person can answer yes or no, and the third one can answer yes or no. They are independent. The selection of the first person will not affect the occurrence or the selection of the second person, and so on. So they are independent. The third thing is, we want to check if how many outcomes are there. Actually, we only have 2 outcomes, whether the person know or does not know. So 2 outcomes. It's 2 possible outcomes. The last thing, every person has the same probability of saying of answering yes. So that's 0.85. So the probability is the same in all stages of that experiment. So the answer is yes. This is a binomial distribution. Now we want to determine n. N is how many people are engaged in this experiment. We have 5. So n is 5. X is number of successes. We are interested in finding the probability that exactly 3 out of 5 answer yes. So 3 is number of successes that we are looking for, and p, probability of success, that is 0.85. And what is q? Q is probability of failure, which is 1 minus probability of success, 1 minus 0.85, and that's equal to 0.15. Now, how to find, if we know that a given distribution is a binomial distribution, how to find probability of that distribution? Now we have a formula here to find probability of getting exactly x successes. This formula is given by this. P of x equals n factorial. This is read n factorial. This sign is read factorial. I will tell you what we mean by this in a bit. Over n minus x, number of trials minus number of successes, all factorial, times x factorial, times p, probability of success, raised to the power x, to number of successes, times q, probability of failure, raised to the power n minus x, number of trials minus number of success. Now the first expression here, n factorial over n minus x all factorial times x factorial, denotes number of outcomes with exactly x successes among n trials. The probabilities to the right here denote the probability of x successes among n trials of any one particular order. Okay, now let me say something about this simple. If we see, now what do we mean by factorial? For example, if we have 2 factorial, if n is 2 and we have n 2 factorial, what does that mean? That means we multiply 2 by all numbers that are less than whole numbers that are less than this given number until up to 1. So I mean, if we have 2 factorial, we multiply 2 by 1, and if we have 3 factorial, that is 3 times 2 times 1. If we have 4 factorial, that's 4 times 3 times 2 times 1. Here we have 2, here we have 6, here we have 24. 5 factorial is 5 times 4 times 3 times 2 times 1. We stop at 1, and that's 120, and so on. So this is what we mean by factorial. Good. Now we can find the probability by 2 methods, either by just computing using the formula or by using the calculator. So if we want to understand the formula, we need to apply it. So let's take an example, the same Twitter example again. Here we have for the first method, we need to determine these things. N, what is N? N is 5. What is X? 3. What is P? Probability of success is 0.85, and what is Q? It's 0.15. And we want to find probability of getting exactly three successes, and that's n factorial, 5 factorial, or just look at this formula here, over n minus x all factorial times x factorial, which is 3 factorial, times probability of success 0.85 raised to the power x here. X is 3 times probability of failure raised to the power n minus x. And then simplifying this, we get 5 factorial over this is 2 factorial, this is 3 factorial, times 0.85 raised to the power 3, 0.15 raised to the power 2. Now here 5 factorial is 120, 2 factorial is 2, 3 factorial is 6, and 2 times 6 is 12, and then 120 over 12 is 10. So we have 10 times 0.85 raised to the power 3, 0.15 raised to the power 2, and then we can use the calculator to find that this probability is 0.138 or 13.8%. That's it. That's the probability of getting 3 people out of 5 people, 3 adults out of 5 adults who know what Twitter is. Now, if we want to use technology, I mean the calculator, we can use this method here, described here in this step, by applying the command binom PDF of n, p, and x. So that's binom PDF of n. N is 5, p is 0.85, and x is 3, and using calculator we should get same answer. Now another example, here we have 67% in a statistics class of students in statistics class have an Android device. What is the probability that 14 of selecting of 20, 14 is number of successes, 20 is number of trials have Android device. So number of successes is to have 14 students who have Android device. So we want to apply the formula. Let's use the calculator. Now here we have percentage. That means this is the probability of success, 0.67, and q, little q, is the complement of this, which is 0.33. Now we apply the formula binom PDF of n. N is 20, probability of success 0.67, and x is 14, and using the calculator we get 0.184. Now another example, here in this example, based on a poll, 60% of adults prefer football over all other sports. Assuming that we randomly selected 5 adults, so 5, this denotes number of trials, and here we have a probability of success, the percentage here, so n equals 5, and p is 0.6 or 60%, and q, so if p is 0.6, q is the complement of that, 1 minus p, which is 1 minus 0.6, that is 0.4, that's q. And here we want to first find the probability that exactly 3 of the 5 adults prefer football. So for part A, probability that x equals 3, exactly 3. Now we use the formula. If we want to use the formula first, we can use n factorial, which is 5 factorial over 5 minus x. X in this case is 3 factorial times 3 factorial times p. P is probability of success 0.6 raised to the power x times the complement, which is q, probability of failure, 0.4 raised to the power 2, 5 minus 3, which is equal to 2. Computing this, we get 0.346. If we want to use technology, we can, or calculator, we use binom PDF of 5, this is n, then p is 0.6 and x is 3, and this will give us 0.3456, or can be approximated to the same answer as the answer obtained from the formula. Now for part B, we want to find the probability that number of adults who prefer football is at least 2. What do we mean by at least 2? At least 2 is probability that x is greater than or equal to 2. We mean by at least 2, 2 or 3 or 4 or 5. So it's x, number of successes, is greater than or equal to 2. Now how to find this probability? In order to find this probability, let's make a table and then find it. So let's take some values for x. X takes the values 0, 1, 2, 3, 4 or 5, because we have 5 people and we want to see if they prefer football or not. Now, what is the probability of x equals 0? Here let's use the calculator, binom PDF of 5, number of trials, and probability of success 0.6, and x is 0 here, so we get 0.010. And we apply same thing here, binom 5.6 and 1 to get 0.077. And let's complete this. For the third, for x equals 2, we get 0.230. For x equals 3, we get 0.346. For x equals 4, we get 0.256. And for x equals 5, we get 0.078. After finding these probabilities, here we have probabilities, and here we have the values of the random variable x. Now we are interested in the probability of x greater than or equal to 2. This is x equals 2, greater than or equal to 2. That means from 2 to 5. That means we need to sum those probabilities. So this is probability of x equals 2 plus probability of x equals 3 plus probability of x equals 4 plus probability of x equals 5. And those probabilities, we just add them to get 0.913 if you find the sum of these. Now, or another method to do this problem, we have probability that x is greater than or equal to 2, that means at least 2, is equal to 1 minus probability of x less than 2. We just exclude x less than 2 from the whole set of values. And this is 1 minus probability of x equals 0 plus probability of x equals 1. So that means we find those two probabilities, probability of x equals 1, probability of x equals 0, and we just subtract them from 1, and that should give me the same answer. So probability of 0 plus probability of 1, and subtract them from 1, you get same answer, 0.913. Now, because probability of 0 plus probability of 1 is, this probability is 0.087. Or you can use the calculator, or we can use the calculator. Probability of x greater than or 2, or if you want to write it in words, at least 2, is equal to 1 minus binom. In this case, instead of writing probability of x equals 0, then probability of x equals 1, we can use another binom, another command. Is this similar to the previous one, but the previous one was binom PDF. That gives you probability for specific value of x. But binom CDF, here we use C, that means cumulative. I mean all values under the given value, the sum of all values under the given value. So we can use this order or command, binom CDF, to find, for example, to solve this problem, 5.06 and 1. Now when I write this, the calculator will find probability of x equals 0 and probability of x equals 1, if we write 1 here. If we write 2 here, it will add probability of x equals 2. That's why we use CDF instead of PDF. This is cumulative, all values that are less than or equal to the given value. The given value is 1, so 0 and 1. It will compute probability for x equals 0 and probability for x equals 1. So this will give us 1 minus 0.087, which is 0.913. Now, binomial distribution is a very important distribution, and from that distribution we can do very easy computations to find the mean, variance, and standard deviation. For example, the mean is given by mu, the mean of the population is n times p. N is number of trials, and p is number of probability of success. And we usually we call this, the mean in this case, we call it expected value, and we denote it as E. So the mean is the same as the expected value. So mu is the same as E. When we ask you to find the expected value, it's the same as the mean, and the mean for this distribution and only this distribution. For other distribution that we will study later, we can't use these formulas here. So these are just true for the binomial distribution. In order to, if you know that a given probability distribution is binomial distribution and you want to find the mean is n times p. And the variance, sigma squared, is n times p times q, number of trials times probability of success times probability of failure. If you want to find the standard deviation, we just take the square root of the variance. Now, binomial distribution usually describes the whole population. Now, unusual results happen. We know that the usual results, normal results, can happen within 2 standard deviations. Here we have mu in the middle, mu minus 2 sigma, and mu plus 2 sigma. Within those 2 standard deviations, all values here are normal, but any value here or value here, it will be considered unusual value or result. Now let's take another example. Here, McDonald's recognition rate, the brand name of McDonald's has 95%. When we see percentage, that's usually denote the probability of success. Recognition rate. And a special focus group consists of 12 randomly selected adults to be used. So this is number of trials. This is n, to be used for extensive market testing. For such random group of 12 people, consider recognizing the brand name as a success and answer the following questions. We want to find the mean for this problem. Now, how to find the mean? We first find n. N is 12, and probability of success, which is 0.95 from here, and that means q, the probability of failure, is 1 minus p, which is 0.05. Now, what is the mean? We know that this is binomial distribution. You can check the 4 requirements, and then you can find the mean. Mu is n times p. N is 12 times p, 0.95, and this is 11.4 people. Now find the variance. The variance is sigma squared equals npq, and that is 12 times 0.95 times q, which is 0.05, and this gives us 0.57 or 0.6 people squared. Because we have square here, we use square here for the unit. Find the standard deviation. The standard deviation is just the square root of the variance. So that's sigma equals square root npq. This is square root 0.57. And then this can be approximated as 0.759498, which can be rounded to 0.8 people. Now find the expected value. The expected value is the same as the mu, or the mean, which is n times p, but we already computed this to get 11.4 people. And the last problem, problem E, we want to use range rule of thumb to find minimum usual member and the maximum usual member of population who recognize the brand name of McDonald's. So to find the minimum, we need to apply mu minus 2 sigma. Now mu is 11.4 minus 2 times sigma. What is sigma in this case? Sigma is computed here. Let's use 0.8, and using the calculator we get 8.9 people. And what is the max? The max is mu plus 2 sigma. As you've seen here, this is the max and this is the minimum. Now the max is 11.4 plus, the negative becomes plus, and we get 13 people. Those are the max and the minimum. Now part F, would 12 be an unusually high number of people who recognize the brand name of McDonald's? 12, now we know that this is the minimum. The minimum is 9.8 and the maximum is 13. What about 12? 12 is here, so no, that's usual. It's usual. It's not unusual.